We'll switch to English as the next speaker, Tommaso Gagliardoni, is coming from Switzerland. As you understood, he is Italian. And so Tommaso Gagliardoni is an expert of cryptography and crypto analysis at Kudelski Security in Switzerland, which is a security-based agency, based company with worldwide scoring. And so we'll speak to us this morning about the bleeding edge between quantum computing and cryptography.
Merci beaucoup. Bonjour tout le monde. Malheureusement, je parle pas français, so I'm sure you will be very happy if I switch to English. In this talk, I will give you a brief overview of the general landscape of quantum computing and cryptography and related topics. And we are going to talk a little bit about what's the situation now, where are we going in the near future, maybe in the long future. So first of all, maybe a little bit of no, the other way. Okay, thank you. The thrill of the honor. So a brief presentation about myself. I studied mathematics in Italy, then I did my PhD in cryptography in Germany. I work with IBM, and I recently joined the Kudelski Security, which is a Swiss cybersecurity company with headquarters in Lausanne. Oh, sorry. But I guess the most important information that you have to know about me is that I haven't been to Italy and I haven't had Italian visitors since last Christmas, okay? And I haven't had any fever or any other strange things, so just to let you know. So I guess all of you have heard about quantum computing and have a broad overview of what it is. I'm not going into the detail here now. The only important point is that quantum computing is a new kind of experimental technology where information is processed through quantum mechanical processes. The appeal of quantum computing is that, in theory, these machines can solve certain problems much more efficiently than classical computers. However, they are very hard to build. That's the problem. So right now, we are still at a very early research stage. We have prototypes. These prototypes seem to work, but it's very difficult to have them scale to useful applications for now. However, what we have seen in the recent years is that the trend is a rapid acceleration in the realization of a quantum computer. And right now we have results that were considered to be science fiction or even impossible until a few years ago. I will talk about this a little bit later. But before saying a lot of nice things about quantum computers, I have to also show some facts that sometimes people tend to forget. So the limits of quantum computing. Because from a practical perspective, it's hard to build a quantum computer. From a theoretical perspective, we already know quite a lot about what these machines would be capable of. And we know, for example, that the theoretical distinction between a classical and a quantum computer is very thin. In particular, any quantum computer can be simulated by a classical computer, in theory. Moreover, we don't have any proof that there exist problems that are inherently hard for classical computers but easy for quantum computers. We know that a quantum computer can achieve a speed up. However, for most problems, this speed up is weak in theoretical terms. And there are only a very few problems that we know how to solve efficiently on a quantum computer, but we don't know how to solve efficiently on a classical computer. So the question is, why all this interest, all this buzz around quantum computers? Why are they interesting? Well, there is basically two reasons. The first reason is that a modest speed up in theoretical terms translates in many practical applications to a huge speed up, which really makes the difference. I want to give you an example. Let's say that I have a deck of 100 cards, and there is one ace in the deck. I shuffle the deck, I give the deck to you, and I say, okay, please find the ace with the least number of draws as possible. How many draws would you need on average to find an ace in a deck of 100 cards? Roughly 50 draws, exactly. Well, a quantum computer can do it with roughly 10 draws. And now you might wonder, well, why is this interesting? Why is this useful? It's nothing cool. Just imagine if instead of 100 cards, you have several billion of cards. And just imagine if you are not dealing with cards, but you are searching for a particular protein encoding sequence in a DNA strand. So it turns out that there are a lot of real-world applications that can benefit from just a modest speed-up. And this is the very first reason why quantum computers are interesting, the civilian application, the real-world applications in many different fields, starting from chemistry, pharmaceutics, finance, any problem that can be modeled as a search or optimization problem can, in theory, benefit from quantum speed-up. The other reason is that I mentioned that we know very few problems that are easily solvable by a quantum computer, but we don't know how to solve with a classical computer. Well, it turns out that these problems are actually super important, because these are the problems which are at the base of the security of most of the cryptographic schemes that we use nowadays. So I would not be wrong in saying that without these cryptographic schemes, the digital infrastructure as we know it today would not exist. So on one hand, we have to see a quantum computer as a resource, as an opportunity. On the other hand, and that's the main reason I am here now, I'm here today, on the other hand, a quantum computer can be a threat. So we really have to keep an eye on the development and the research trend in quantum computing. Luckily, we already have countermeasures for this threat. And these countermeasures, in terms of defending our cryptography against quantum computer, can be divided into two broad categories. One category is quantum cryptography, and the other category is quantum safe or quantum resistant or post-quantum cryptography. Let's have a look at them. I will start with quantum cryptography, which itself can be divided in two broad categories. And I'm talking about this because sometimes there is a little bit of confusion about the terminology, okay? So quantum cryptography is the use of quantum mechanical processes to defend information or to process securely information, let's say. And it can be divided in general, fully fledged quantum cryptography. And this is the use of a quantum computer to protect data. So we are talking about cryptographic algorithms that do not run on modern hardware. They run on quantum computers, and they are used to protect classical or quantum data. I mean, clearly, since they have to run on a quantum computers, we don't have this kind of cryptography yet, because we don't have yet quantum computers powerful enough to deploy this kind of cryptography. Which means that right now, this topic is of limited applied interest. It's more something that will come maybe in the future. But I mention it because it's going to be very important in the moment that we have quantum networks. Because if history tells us anything, is that whenever you have a new kind of computing technology, the next step is that people want to network these machines together. So as I will mention later, there is already ongoing research on quantum networks. That is the possibility of connecting quantum computers through optic fiber or laser channels or whatever. And in the moment when you start exchanging quantum information, you need new kind of cryptography to deal with this scenario. Because quantum information behaves very differently from classical information. For example, you cannot copy data. So you cannot make a log of the traffic or similar application that we give for granted in the classical world. So the other application is quantum key distribution. Quantum key distribution is a a special case of quantum cryptography. This is something that exists nowadays. You can buy it. It's commercially available. It is a little bit, I mean, you need special hardware for this, but it can be realized today. I have read there was some news that I've read yesterday about a new achieved the record of the maximum distance for point-to-point land-based quantum key distribution, and we are now at 500 and something kilometers, which is already interesting. Quantum key distribution is not a silver bullet, okay? So it has some points of strength, but it also has some drawbacks. In particular, it can only solve one specific problem in cryptography, the exchange of symmetric keys between 2 points. If you want to encrypt data at storage, if you want to do signatures or other cryptographic applications, this is of no use. You have to add something else on top of it. And then there is the other aspect that we were talking about, the quantum-resistant cryptography or quantum safe. I personally don't like the name post-quantum because I consider it a little bit misleading. So the idea of post is that this would be cryptography secure in a world after quantum computers have been realized. But this is a bit misleading because, as I will show in a bit, quantum-resistant cryptography is something that we have to look at now. So we don't have to wait that quantum computers become available, because it's very crucial that we start securing our cryptography now. Otherwise, it's going to be too late. Quantum-resistant cryptography is cryptography in the traditional sense, so you can run it on your smartphone. But it's based on mathematical problems that are so hard, so difficult, that not even a quantum computer is believed to be able to break this kind of cryptography. Which means that it's a very secure form of cryptography, but it also has some drawbacks, because, for example, it is a relatively recent research topic compared to other forms of cryptography. And therefore, it is currently very hard to assess the security. So, for example, if you want to know how large should my key be in order to withstand attacks for the next 50 years of quantum computing, these are difficult research topics, and there is a lot of discussion ongoing on this. There is also the problem that quantum-resistant cryptography is not a one-size-fits-for-all solution. There are very different flavors of quantum-resistant cryptography, and they are all very different in terms of performance. Some of them are very fast, but they have huge key size, for example. Others have compact sizes, but the security is not well understood. Others are very secure, but you can only do signatures with them, for example. So the situation is a little bit more complicated in respect to traditional cryptography. And this is the reason why in 2016, the NIST, the American Technological Standard Institute, they started a post-quantum competition for standardizing quantum-resistant cryptography. This is the same kind of process that led to the standardization of AES and SHA-3. It's a long process, so we are still expecting 2 to 3 years before the end of the process. There is probably going to be some fast-track procedure for standardizing certain kind of cryptography. But what we expect is that, unlike the case of AES and SHA-3, there's not going to be one single winner out of this competition. And the reason, as I said, is that different kind of quantum-resistant cryptography have very different applications. So we are probably expecting that there's going to be a winning suite of quantum-resistant algorithms for different uses, IoT, signatures, or whatever. But the crucial point is that it's very important to act now. So we don't have to wait that quantum computer become a threat. And the reason is the following. So consider the time that you need to research and standardize the new cryptography. Consider the time that you need to deploy your cryptography on the field. And then consider the time that you require your current products or services to remain secure, even if they are quantum vulnerable. If the sum of these three time frames is longer than the time required to build scalable quantum computers, you are in big trouble, because it means that you are already late now. And in fact, what you see in this picture is, this is a data center of a famous three-letter agency that I will not mention, but I give you a spoiler, this is based in Utah. And this facility is designed to store exabytes of data. Exabytes is, like 1 exabyte is 1,000 petabyte, 1 petabyte is 1,000 terabyte, and 1 terabyte is 1,000 gigabytes. So they are basically storing all the internet traffic. And the idea is that even if this traffic is encrypted, they say, one day we might be able to decrypt this data. And when this day will arrive, for some of this data, it's not going to be useful anymore, but for some other data, think of military communication, diplomatic secrets, that's going to be valuable. Now you also add to this consideration the fact that many products on the field and many services need very long assurance time. Think of smart cars. I mean, from the point where you start designing a smart car, you build it, you put it on the road, and then all the lifetime. I mean, how much time is going to pass? 30 years, maybe? 40 years? We are probably going to see interesting advances in quantum computing before that point. And certain data require even longer assurance. Think of genomic data. This is kind of information that has to be, it's required to be secure for a period of time even longer than the lifetime of the owner of the DNA, because, you know, this is information that is also impacts your the future generations. And right now we are still at time frame A. So it's really time to look at this very quickly. So I am running out of time. So what I want to say is that right now the situation in quantum computing is that we have prototypes. Counting the number of qubits of quantum memory is a very bad idea. It's not very meaningful. But you can start playing with quantum computing in the sense of, you know, writing software for quantum computing is very different than writing software for classical computers. And there are cloud applications or simulators where you or your scientists, your technical personnel can start practicing now, so in order to be ready when quantum computer arrives. There is a lot of big players in the field that are investing in this technology. We are talking about, you know, Intel, Google, IBM. There is a famous company that you probably heard in the news that is D-Wave. D-Wave is advertising this 5,000 qubits quantum computer. The point is that it's not a real quantum computer. It's a kind of a different machine. So you cannot use this machine to break cryptography, just to be clear. And then you probably have heard about quantum supremacy in the news. This was a big thing, and there was this argument between Google and IBM. Again, I don't have time to go into the detail, but what happened is that Google used their prototype of quantum computer to solve a problem that would require a huge amount of resources with a classical computer. And this was a big thing because it was the first time that somebody gave a real demonstration that a quantum computer could do something that normal classical computer would struggle to. Okay, what do we have to expect? So the road to a fully quantum world is quite long, of course, but we have seen a lot of progress recently. We know that breaking cryptography with quantum computers would require a huge amount of resources that we do not have now, and we are nowhere near to achieving. However, you have to look at the trend, and the trend says that we are getting closer and closer. And you also have to consider another thing, that there is this technology, which is called quantum error correction, that is very interesting, and this is something people usually don't really look at in the outside of the quantum computing field. Quantum error correction is a technique to bundle a bunch of noisy qubits together into a single logical qubit that self-corrects itself over time. When we arrive at this step, this would be the holy grail of quantum computing, because at that point, so currently the difficulty in scaling the number of qubits is that the noise increases, and after a few milliseconds your computation is trash. But if we arrive at this threshold, scaling a quantum computer becomes much easier. And with the current technology, this threshold is around 1,000 qubits. And given that we are already in the order of 50, 100 qubits, that's not too far away. So this is something that we have to consider. Yeah, as I said, RSA, elliptic curves, traditional cryptography, all public key cryptography is all broken. Elliptic curves are even more vulnerable, so keep this in mind. Yeah, symmetric key encryption and hash functions were commonly believed to be mostly immune to quantum computing, or let's say easily fixable. However, recent research in the last few years started to challenge a little bit this scenario. And we are at the point that we also have to start worrying about the security of symmetric key encryption and hash functions. There is quantum networks research, and then there is the civilian applications, as I said. And remember that civilian applications will probably arrive before cryptographic use of quantum computers, because they require less resources. So useful, like real-world useful applications of quantum computers will arrive already at around 100 qubits, application in chemistry. Okay, very quickly, what we do at Kudelski Security in this field. We don't build quantum computers yet. However, our company is focused in, building all-around security solutions, and in particular, what we do, and we are starting to, present these activities starting from this year. So we have a lot of experience in risk assessment, and now what we are proposing is an all-around consultancy service to, look at your exposure, build a profile of your risk, and say, for example, well, you have a certificate which is based on RSA, but it's expiring in 2 years, no risk. But you have the master key of your certification authority with a 20 years lifespan. This is going to be a problem. You have to change it. This kind of analysis. We build a profile. We rank the severities that we find, and according to the severity, we propose countermeasures. Secure code audit. So you have cryptographic code that wants to use quantum-resistant cryptography. We give you a security audit of it. White papers, quantum trainings, both in the field of quantum computing for scientists and quantum attacks on cryptography. And then we also do benchmarking of QKD devices, quantum random number generators. It's very important to benchmark the security of these applications here. So this concludes my talk. If you have any questions, please reach out to me. I don't know if you have time for questions now, but if not, just reach me up at the coffee break.
We are running a bit out of time, but maybe we have time for one question from the room.
Are you referring to attacks with quantum oracles on operating modes and things like that?
Correct. We are looking, for example, at quantum superposition attacks that are not considered usually in the traditional post-quantum scenario, because you are like, well, you know, my scheme is classical, why should I have quantum access? So the reason why people are looking at this is, there is a bunch of reasons. The first reason, for example, is what if you want to use your symmetric key encryption scheme as a building block to encrypt quantum data? And in this case, there is not a straightforward transition from the classical case to the quantum case. But there is also another very important reason for real-world implementations, and this is the quantum fault injection attacks. So in this kind of attacks, just look at classical fault injection attacks, okay? You have a smart card. This smart card has some secret key in a tamper-proof area of memory. And what scientists do nowadays is that they take your smart card, they start shining lasers or measuring the thermal output and power consumption, and this leaks information. This is something that also Kudelski Security is doing from a forensic point of view. So it was considered science fiction 30 years ago. Nowadays, you have to design your hardware with this in mind. Quantum fault injection attack are a similar concept where there is the possibility that if you take your classical hardware and you start freezing it at very low temperature, isolating it from the electromagnetic noise, and doing some modifying the physical behavior of it, there is no guarantee that you don't start to witness at least partial quantum behavior. Why this is of a concern? Because even for modern hardware like Intel CPUs, for example, we are already at the scale of 7 nanometers or so. At this scale, quantum effects are real. And in fact, when you design a CPU, you already have to build your circuit in such a way that the quantum effects don't make an electron jump from one gate to another. So these systems are delicate. And it's not science fiction to think that in the near future, we will be able to force these quantum errors to extract information from the devices. And this model, this attack scenario, is not considered in traditional post-quantum security. This is why we also want to look at quantum superposition resistant symmetric key and dash functions.
Okay.